Okay. Good afternoon, everyone. Today is the last class of this mini course. Before going to the class, I want to make a propaganda about a workshop on optimization. It's the first Carioca workshop on optimization and application. It will be held in May. It will be held in May at FGV. Okay, at FGV, and up to now we have 5 plenary speakers has confirmed for the invitation. Alfredo Isium from FGV, Binar Sveiter from IMPA, and Azon Danfazil from Meta US, and Regina from Australia, Alejandro from the CMM from Chile, and we also invite some other very famous mathematicians, optimizers for this conference. And this conference is also to honor the 75th birthday of Alfredo. The topic of this workshop is to combine or to put people from optimization, machine learning, and industries together to increase or to generate ideas among these topics. And we offer 2 mini courses. One from the applications, such as, for example, here is from optimization methods for the tensor factorizations. It's more related to the applied methods and problems. Another will be from a more theoretical part in optimization, and we also have sections of posters which we encourage students, undergraduate students, PhD, master students, PhD students to take part in this section to present your ideas, your papers, publications, anything you want, and we will give a junior award for the best presentation in this section. Okay, and the date here. The date here, I think is here. Let me see. It's from 5th to the 8th in May at FGV about this workshop. Okay, next let's go back to our course. In this course, we have discussed about maximum monotone operators and its corresponding monotone equilibrium problems. We mentioned a lot of problems in optimization can be regarded as a special case, such as optimization problem with constraints or without constraints, and variational equality, and like feasibility problems. So in one word, it's a very important but somehow a little bit abstract problems. And later we studied the most important algorithms, the approximate point method, okay, for solving the maximum monotone equilibrium problems. And in the last class, we introduced the splitting method, okay. So we make a summary about the last class. First we want to solve this equilibrium problems, the sum of 2 maximum monotone operators, okay? Instead of using the PPM, which is the proximal point method, because if you use proximal point method, the iteration would be like the resultant of A plus B xk, which equals to the identity plus the lambda A plus B inverse of xk. Generally speaking, the resolvent or the inverse of these operators is not very easy to calculate, even if we assume not only A and B are maximum monotone, even if the sum is maximum monotone. So our idea is, can we split these problems into smaller problems or smaller parts, like instead of using the resolvent of A plus B, is it possible to use resolvent of A and the resolvent of B, or sometimes we use the operator directly, like the operator A or operator B. But if you use the operator directly, you need to assume that this operator is single valued, okay? So compared with the resolvent of summation, usually this kind of resolvent, sorry, this should be B. The resolvent of independent operators would be much easier to compute. So based on this fact, we proposed splitting method for these inclusion problems. Like first we have FBS, okay, which is called backward splitting, which is based on the fact that if 0 belongs to A plus Bx, which is equivalent to 0 belongs to I plus identity of B and minus identity plus identity minus lambda of A x, okay, and we define they equals to no, we do not, and this is equivalent to the I minus A x belongs to I plus lambda B x, okay? So if we assume A and B are maximum monotone, then we can calculate the resolvent of this operator. So it is equivalent to say that x equals to the identity plus lambda B inverse I minus lambda A x. Okay, so this is equivalent to x equals to the resolvent of B and I minus lambda A x. Okay, so if a point x is a 0 of, this is equivalent to say that x belongs to the 0 side of A plus B, okay? If x is 0 of A plus B, then x is a fixed point of this operator, okay? So we define this operator as t. Then we can use the fixed point iteration with respect to this operator. So we get the FBS. FBS iteration is xk plus 1 equals to the resolvent B I minus A xk. Okay, so this is the iteration of the forward-backward splitting, okay? But here we have some summations of the algorithms. First, that A should be single valued, okay? Because you use the I minus lambda identity here. You use it directly, so you need to make sure this is determined. And then for the convergence, we also need to assume that A is co-coercive. Because if A is co-coercive, then we know this operator is what we call averaged, okay? It's averaged. Then we already know that the resolvent of a maximum monotone operator is average. So the composition of two averaged operator is still average. So this iteration converges to a point of fixed point of this operator, okay? And corresponding, we also have BFS, which is called backward-forward splitting method, okay? And it works like xk plus 1 equals to I minus lambda A, the resultant of bxk, okay? The difference is the order. We perturbed the order. First do the resultant, and then we do the we evaluate with the operator A. Here you need to also assume that this operator is a single valued, okay? Is single valued, and up to now we have two kinds of splitting schemes. First is this FBIs, okay, here, and the second is the BFS. In these two splittings, what we used the resultant of B or resultant of A and I minus identity minus lambda A and I identity of lambda B. But we didn't use these two resultant together. So next we have this called double backward splitting, okay? Because here you use one resultant, one operator directly. One resultant, one operator directly. So why didn't we use the resultant together? Okay, or the composition of the resultant. So the double backward splitting is somehow xk plus 1 equals to the resultant of B composition resultant of A xk, okay? By the knowledge of averaged operator, we know the composition of two resultants of maximum monotone operator is a still averaged operator, okay? So obviously this sequence will converge. We can conclude that this xk will convert some x star which belongs to the fixed point of the resultant composition. But this x star will be the solution of zero site of A plus B. This is a problem. Unfortunately, we cannot guarantee that the limitation of this sequence which generated by this double back forward splittings is a solution of the inclusion problems. Okay, we cannot guarantee that, but it could be used to find that 0 belongs to problem like this. 0 belongs to AX intersection with BX. It can be used to solve this kind of problem, the common 0 point of two maximum monotone operator, okay? Because the 0 site of A plus B is not identity with the fixed point of the composition of the resultant, okay? So up to now we have forward, backward, backward, forward, and double backward splitting. At least this forward, backward, and backward, forward works. And in the at the end of the last class, we talk about the Peaceman, Douglas, Hartford splitting. Okay, what is this family of splitting method? Instead of using the resultant and the operator directly, we recall that the reflection operator of A is defined by two resultant of A minus the identity similarly the reflection of B equals to 2 resultant of B minus I, okay? So the idea is instead of using resultant, we're using reflection. So we give a family of splitting that xk plus 1 equals to 1 minus rho k over 2 identity of xk plus rho k over 2 reflection of A composition reflection of Bx. Okay, or we can write it, yeah, okay, this family. And it's a kind of or we can write it in this way. This is identity. Okay, so it's a convex composition of the composition of two reflection with the identity. Okay, here if the rho k equals to if the rho k equals to 2, this operator is just the reflection. Okay, the operator is reflection of A and the reflection of B. This fixed point operator becomes this. This is, we call it Piesman Hashford splitting, PRS. If the rho k equals to 1, then the operator is 1 over 2 identity plus 1 over 2 R lambda A, R lambda B. Okay, this is what we call the Douglas-Hashford splitting, DRS. Okay, so at the end we introduced two splitting which based on the reflection. Okay, let's continue analyze these two splitting. Okay, first we analyze the PRS. Okay, so if there x belongs to 0 of A plus B, we conclude that we have Z belongs to the fixed point of the composition of reflection. Okay, and x equals to the resultant of Z. This is the last conclusion we get in the last class. From this result, we expect if this algorithm works, we do the iterations with fixed point iteration by this vector. Okay, the reflection A, reflection B, xk. We use zk here. Sorry, we use zk plus 1 and zk, and we expect that first zk converts to some z star. Okay, and this z star belongs to the fixed point of this double reflection, and then we do the corresponding sequence xk converts x star. Okay, and this x star belongs to the 0 set of A plus B, which is the solution of the inclusion problem. This is what we expect to have. But the problems here is the second conclusion, or is the first conclusion. This is okay, because we have analysis that if there is a fixed point, then we do this. We do one more resultant. Then this xk will belongs to the solution site. But the problem is this: we cannot guarantee the convergence of this zk. Okay, the problem is the property of this resultant. Okay, let's go back to the definition of the resultant or definition of reflection. What is the definition of the reflection. Reflection is 2 times the resolvent minus I. So here, if A is maximal monotone, we know that the resolvent is somehow 1/2 averaged, okay, or firmly non-expensive. And then we can know that this reflection is just non-expensive, okay, non-expensive. And this is also non-expensive, and then the composition is also non-expensive. But unfortunately, this non-expensive operator cannot guarantee the convergence. For example, you can recall that for example, this kind of rotation operators is non-expensive, but if you give any point in the R2 plane, which is not the 0 point, it will not converge, okay? So this cannot be guaranteed. So this splitting or this fixed point iteration with the Piesman-Hirschfeld splitting doesn't work usually. So the idea is here we want to improve this splitting. Since we already have non-expensive, okay, this operator is non-expensive. But the good thing is the fixed point is okay, it's related to the solution site which we are interested. We just need another projection step, or we can say we do another resolvent step. So the only problem is we need to improve it in order to guarantee that the sequence will converge. So we do just so the problem is how can we get a operator from non-expensive to averaged, because averaged can guarantee the conclusion, okay, or can guarantee the convergence, and didn't make any change of the fixed point side, because this fixed point side is what we want. So the answer is we make the convex combination. So this is the R lambda A, R lambda B. We make a convex combination with identity and with 1/2, okay, 1/2. Because this 1/2 makes the fixed point of this operator is an identity with the fixed point of this operator. So we can imagine if we do the fixed point iteration with this operator, if we get a point in the fixed point side, then it can be related to the 0 side of A plus B, okay? But this operator, we can say it's averaged, because by the definition of the averaged operator. So this somehow is the iteration which we want. This is what we called the Douglas-Hirschfeld splitting. And we can have the conclusion in the finite dimension space that, sorry, I should use the zk here, okay? I use the z here. So first we have this zk converts to some z star which belongs to the fixed point of this operator, and also the fixed point of this fixed point side of this operator is identity with the fixed point side of this operator. So and the second result is that if we do a resolvent on both sides of this limitation, why we can, for example, we do the resolvent here, okay? We do the resolvent of course, okay, this is a relation between x and z. Second, if we have this, we do the resolvent on both sides of this limitation. Okay, then we get this is xk, another sequence, and this is x star, okay? And this x star belongs to the 0 side of a plus b. The reason why we can put this resolvent on both sides of this this limitation, because that this resolvent is continuous, okay? Because we know that the resolvent first is firmly non-expansive, okay? Firmly non-expansive. Then we know that it's Lipschitz continuous. So it is continuous, so we can do this. Okay, up to now, this is what we have discussed last class. Then we go to what we continue from here. Okay. Okay, so this is a Douglas-Hushford splitting. Okay, and then it can be written this way. Okay, it can also be written in this way. If we expand this part, okay, actually when you read papers about the Douglas-Hushford method, you can see several equivalent statements of the algorithms, okay? So if we expand this operator here, okay, this 1 over 2 r lambda a r lambda b plus 1 over 2 identity. So we can have here is 1 over 2, by the definition it's 2 times resolvent A minus I, and times 2 resolvent of B minus I, and plus 1 over 2I. So by very easy calculation, you can have it's equals to the resolvent of A, and the input is 2 resolvent of B minus I, and plus the resolvent of B minus I, if I'm not wrong. Okay, so first, to evaluate this operator, so first step, if you have a zk here, okay, if you have zk, first you can calculate the resolvent of B, okay? So we can define this as somehow xk plus 1 over 2. Xk plus 1 over 2. And then xk plus 1, 2, we can define it as this one, okay? So it can be written as the resolvent of A, and this is 2xk plus 1 over 2 minus xk, okay? And the second and the third step is we need to combine this and this together. So the next point, zk plus 1 is just equals to, this is xk plus 1 and plus xk plus 1 over 2 minus zk, because these are corresponding to the zk. Okay, so I think here is a minus. I think it's minus. So here is minus and plus. Okay. So if we just expand this composition of reelection operator by the definition, we can have these 3 steps statement of Douglas-Hushford method, which are equivalent to the statement here. Okay, this is a convergence. For the resolvent step size, we have no restriction. We just assume the inclusion problems has solution. Okay, this is we have analysis. We have analysis before on the blackboard. Okay, here we give an application of DRS for the convex optimization problem. We give a primal dot problems pair. The primal problem is minimize the f plus g, and this is corresponding to corresponding dot problems. It's a maximum with the dot variables u. Okay, they can be generated by this convex concave function Lagrange. Okay, this Lagrange where f and g are CCP function. If the total duality holds, which means the optimal value of primal problems and dot problems exist, and they are equal. They equal each other. Then the primal problem is equivalent to find the zero of this the sum of the subgradients, which is the inclusion problems. Okay, it's because if f and g are CCP function, then the subgradient of f and subgradient of g are maximum monotone respectively. Okay, so we can use the DRS for this maximum monotone inclusion problem of summation. So we can have this. How do we get here? Okay, we recall that here. If we have a CCP function f is CCP function, then the resolvent of f is just the proximal operator of f. Okay, so by this we have the DRS of this convex optimization problem becomes these three lines. First is a proximal step with respect to g, then respect to f, and then put them together. Okay, by the definition of Douglas-Hartford splitting. If the total duality holds, we have that the xk converges x star, and the xk plus 1 to converge to x star, and the k converges to z star, which equals to the xk plus alpha plus the limited point of the door problem. Okay, let's recall. We have we also utilize another splitting method, which is a forward-backward method. Okay, forward-backward method for this primal problems, which means to solve these inclusion problems. Let's recall the form of it. So if we want to solve 0 belongs to, but here we make a difference. We assume that f is differentiable. Okay, we want to solve this inclusion problem, and we use FBS, forward backward splitting, which is xk plus 1 equals to the resolvent of b of a and I minus identity a. This should be b. Anyway, here a should be single valued. Obviously, this is single valued, okay, because it's a differential. It's a differential, so it's a sub-differentiable. Sub-differential is a singleton. So we use the FBS for this problem. What we get? We get xk plus 1 to the actually first this becomes the gradient. Okay, so it's the lambda, the gradient of f xk, and the second step we do the resolvent with respect to b. B is a subgradient of g, so we have the proximal operator of g. Okay, so this is how we get the proximal gradient. Okay, proximal gradient. Actually, what is proximal gradient method? Is this? It's just the FBS for the convex for this problem, which is optimal condition of the convex optimization problem. We compared these two forms. DRS. Okay, we first saw DRS. In these 3 lines for DRS, we need to solve 2 sub problems, which is minimization of G and minimization of F, okay? But for the step size, there is no restriction. And we do not require F is differentiable. So we have less restrictions. But on the other hand, we need to solve 2 sub-problems. And for the, let's go back to the proximal gradient method, okay? It's here. We just need to calculate 1 sub-problem, okay? We just need to solve this. It's the argmin of gx plus 1 over alpha z minus x squared, okay? This is the proximal of g at z. It's argmin problems, okay? In this problem, which is the proximal gradient method, we only solve 1 proximal sub-problem because this is has closed formula, okay? Because we already know how to evaluate the gradient of f. But the convergence of proximal gradient method requires more more assumption that we require f is not only differentiable but smooth, okay? So the gradient is Lipschitz continuous, and we have more restriction on the step size. So there is a restriction here. So if you don't have the priori knowledge of the Lipschitz constant, you need to have a try before the iteration, before the algorithms to know good options of the step size. Okay. So generally speaking, the DRS are used for when the resolvent or the proximal operator of f and g, they are easy to be calculated independently. And the proximal gradient method are used for when you know how to evaluating the gradient of f and the proximal of g. And the PPM are used for only when evaluating the sum of the proximal operator of sum of f and g are easily. Usually it's difficult in the practical case. Later, now we give a more concrete example, which is the Lasalle problems in the statistics, which is minimize the sum of these 2 terms. First is the smooth term, and second is the penalty term in normal 1. Okay. So we can use what we, because it's optimization of summation of 2 convex functions, CCP function. So we can use the DRS we analyzed in the previous slides. Okay, it has 3 lines. Okay, first we calculate the proximal operator with respect to this function. Okay, but since this function is smooth, you can have the closed formula of the proximal. We go back. So first you calculate the proximal operator with respect to the g, which is argmin problems. Okay. So first we calculate the argmin of this function, okay, the proximal sub-problem of this part. Since it's differentiable, we can have a closed formula. It's the multiplications by 2, it's the inverse of this matrix multiplied by this zk plus alpha A transpose B. And then we do the second step is the S of this at this point. The S is called the soft thresholding operator. It is here. It's just the proximal operator with the 1 norm. Okay, it's the L1 norm. Generally speaking, this step is also cheap in the sense of computation. It's not expensive, so it could be easily to evaluate. And then we, by the definition of the Douglas-Hartford, we put them together. And of course, we can also use the FBS, which is a proximal gradient method, okay? And if we use a proximal gradient method, since this part is differentiable, okay, this part is differentiable. If we use the FBS or proximal gradient method, it's just 1 step with respect to the operator S, which is a proximal operator with respect to this at this point, okay? And as I mentioned, this operator is cheaper in the sense of computation. So we can compare the two iterations for these Lasso problems in statistics, okay? The DRS requires the inverse of this matrix, which is not so good because the inverse would be very expensive if the dimension of the matrix A, M, and N are very large, okay? So FBS is cheaper in the sense of computation, okay, because it avoids calculating of the inverse of any matrix with big dimension, okay? And the method, okay, and this method is called the iterative shrinkage thresholding algorithm, ISTA, okay? And all this splitting together with fixed point, as we mentioned before, are called the fixed point encoding. Okay, this fixed point encoding, approximate point method, forward, backward, forward, Douglas-Hartford, they all established the correspondence between the solution of a monotone inclusion problems and the fixed point iteration, fixed point of a related operator, which means we use the fixed point iteration with respect to our operator, okay? And the fixed point of this, the fixed point are the corresponding as a solution of the corresponding problems we are studying. Why it's the resolvent, not the I minus alpha A, okay? Because generally speaking, the inverse of identity minus some subgradient is often difficult, and the plus is easier, okay? And we also use single-valued operators because it's more actionable, and in the computer you cannot restore a site, but only a vector, okay? But the multi-valued operators somehow like the relations. You can, if you read some papers about the splitting method, like Douglas-Hartford method or the Piesman-Hartford method, you can see some algorithms are represented by the multi-valued operators, or in the sense of relations. But they are useful in the mathematically. In the practically, we prefer use the single-valued operator. Okay, we give a short history of the convergence of the Douglas-Hartford method, or Douglas-Hartford splitting. It was first proposed by the Douglas and Hartford for solving a heat equation, okay? And then Lyon and Mercier, they used this splitting for optimization problems or inclusion problems. Then Exton and Bertesecas studied the perturbed or relaxed form of Douglas-Hartford method, and until 2019, Zweiter-Binar solved the weak convergence, totally solved these problems and closed the door, okay? And this is the beginning. This boundary problems of the heat equation R2, okay? And they used this scheme to solve these problems. If we define A equals to the minus, B equals to the minus grade Y square. If we use this definition, we can transform this scheme to this scheme, okay? We use A and B here, and we use the definition of the resolvent, okay? We can rewrite this in one equation. It's UK plus 1 equals the identity plus B inverse and blah, blah, this, okay? But there is a problem here. If we assume A and B are maximum monotone operators, they are probably multi-valued. So this operator, I identity minus lambda B, could be multi-valued. So this could be it could be confused in the iteration. So we prefer the single valued operators, okay? So we choose B belongs to the capital B UK, and then we can, and we choose VK equals to UK plus lambda KB, and such way that UK can be equals to the resolvent of B VK. And this comes from the Minty theory, okay? So if we change the variables from UK to VK, then this iteration becomes this one, okay? Becomes to this one. And this is equivalent to what I write here, okay? This is what we are familiar with. This is the form we are familiar with of the Douglas-Hartford method, okay? So in this sense, okay, we talk a little bit here. In this form, everything is determined. Every operator is single valued. The resolvent, 2 times the resolvent minus A, I minus the resolvent. Everything is in single value, so it's well-defined iteration, okay? And in this paper, Lyon and Messier in 1979, they proved this iteration converge, but with the assumption that not only A and B are maximum monotone, but also the sum of them are maximum monotone, okay? And then we go to the paper by Axton and Bertasekas in 1992. So we can also define this is the operator of the DRS, okay, or Douglas-Hartford splitting. We define it as G lambda AB, okay? So the Douglas-Hartford recurrent could be rewrite as this, okay? This is the fixed point iteration with respect to this operator. And we consider the operator S lambda AB, which is the inverse of this minus identity. So they proved that if A and B are monotone, this S lambda AB, we go back. This SAB is just the definition, the inverse of G. The inverse of the Douglas-Hartford operator minus identity. If A and B are maximum monotone, then this SAB are maximum monotone, okay? And if A and B, actually, this should, we need to also, we need another assumptions here. If A plus B are maximum monotone, the summation are maximum monotone, then we can see that the G, you can also rewrite G is the identity plus the S inverse, okay, is firmly non-expansive. It's firmly non-expansive. And we can prove that the 0 of S is a subset of the 0 of A plus B, okay? Then it is very interesting that if we do the ZK iteration with respect to the operator ZK by this form, which is the operator G, actually it's the Douglas-Hartford operator. It is equivalent to this. Sorry, there is a typo here. It should be XK. It is equivalent to do the iteration with respect to the inverse, to the resolvent of S, okay? And in this sense, they claimed that actually the Douglas-Hartford method is a special case of the proximal point method, because here it's a proximal point method, okay? It's a proximal point method which use the resolvent of the operator S lambda AB, and if A and B are maximum monotone, if A and B are maximum monotone, we know that SAB are maximum monotone. So this iteration is just the proximal point iteration for the maximum monotone operator S lambda AB. So we say the Douglas-Hartford method can be regarded as a special case of proximal point method. And in this paper in 1992, okay, they proved this perturbed Douglas-Hartford method, okay. So as we analyze the approximate point method in our first class, here we can also calculate the resolvent with arrows, okay? We can calculate the resolvent with respect to A, also with arrows alpha k. If we assume that these two arrows are summable, and if the solution set is not empty, A and B are maximum monotone, and the summation is still monotone. This is also necessary for the paper by Exton and Bertelsecas. Then they prove that they can convert to some solution of this set, okay? And this is the solution set of the original problems. Okay, so this is what Exton and Bertelsecas has did in his paper. And let me make a summary here. All the summations, both in this paper by Exton and Bertelsecas or in this paper by Leon Mercier, they analyze the convergence in Hilbert space, which means, generally speaking, it's weak convergence. Okay, because as I mentioned before, the resolvent is continuous in the finite dimension space, but it's not weak-to-weak convergence in the Hilbert space. So the summation are always required from the beginning of the Douglas-Hartford method until the paper by Zweiter in 2018. Okay, because in this paper they do not he doesn't require the summation a maximum monotone anymore. Okay, but he used the definition, the idea of extended solution set. Actually, in the proof by Zweiter, the proof is not in the original space, which means has the same dimension with the variable. It's in a higher dimension. And the ideas come from the projective splitting method, which we will introduce at the end of the class. Okay, so 1979, they require summation is maximum monotone, also here, but in 2011, we do not need the summation anymore. Remember, all the convergence in this slide, in this page, are weak convergence. Okay, next we derive the ADMM. It's also application of the DRS, okay? We can derive the ADMM from the DRS, okay, by the technique which we call it infimo post-composition. What is that? It has two steps in this kind of techniques. First, we want to solve this kind of problems. The objective function is the summation of CCP functions. We have f, g, h, etc. And the constraint is a linear equality. Okay, ax plus maybe by equals c. Okay, and this equivalent to somehow this is called infimo post-composition of f by y. Okay. And then we use, we can convert these constraint problems to unconstrained problems with summation of many functions like this. Okay, and then we use the very basic splitting. So what is the infimo post-composition of f by a? So it's just the infinite of f such that ax equals to z. Okay, here f is a function from Rn to R union with the infinity, and A is a matrix. So the infimo post-composition IPC of f by y is from Rm to R union the infinity. Okay, it's also called the image of f under A. And if f is CCP and with this regularity condition, then we know that the SCP of f by y is also CCP. If it is CCP, then the subgradient is maximal monotone. Then we can use what we have learned before, okay? So next we introduce two identities of IPC. First, it's the conjugate of the IPC f by a is equals to the conjugate of f. Actually, this identity explains why this informal poster composition IPC appears in the convex optimization, because this kind of form conjugate appears frequently in the door problems of in the primal door problems, actually in the door problems, but the primal problem is usually a convex optimization problem with linear constraints. Okay, so first we prove this. By the definition of conjugate, we know that the conjugate of a CCP function is just the supranu of inner product minus the function itself. Here we use the definition of the IPC of f by a. Okay, it's just a definition. Here the supranu is in sup is in z. Okay, and then it is equivalent to calculate the infinu minus infinu. Okay, and here we know this part has nothing to do with x, so we put the infinu of x outside, so it's the infinu of x and also y, also z, of this f plus the indicator function minus this inner product. Okay, so before we take the infinu of x, we first take the infinu of z, and by this equality here, we know z could be write as ax. So this is u inner product with ax. Okay, and by the definition, this is just the conjugate of f and with the inner input of a transpose u. Okay, so this is the first identity of IPC, which explains why the informal post composition is useful in convex optimization. And this is the second. Okay, it tells us if we calculate the proximal operator of the IPC of f by a, it's just the minimizer of x with respect to this function, and then let z equals to ax. Okay, so the argument of this part is maybe not unique. Okay, it may has several minimizers, but z is unique because this is equality here. Okay, so by these two identities, we can derive the ADMM by the DRS. Okay, so we consider this primal problem. The objective function is a separable of summation of two convex functions. Here you see why it is separable, because this is x and this function is respect to g, and the constraint is a linear equality. And the door problem is this, and this primal door pair could be generated by this Lagrange. Okay, and we have this regular we have this kind of regularity conditions. We can guarantee the IPC of f by a and IPC of g by b could be CCP function. Okay, and this is the definition of the Lagrange, which we will use in the later slides. And the Lagrange, the augmented Lagrange is just Lagrange plus this penalty term. Okay, so the primal problems of this primal problem is equivalent to this problem. We introduce another variable z. Okay, so it's minimized with respect to z, x, and y. Okay, and we divided these constraints to two parts. Okay, we have two linear constraints here, and we use the IPC we discussed before. So this part is this constraints problem is just equivalent to minimize of summation of two IPC. Okay, first IPC is of f by a of z, and second is g by b of z minus z. we define this function is f tilde z and this function is g tilde z. So the primal constraint problems becomes these unconstrained problems, okay, by the techniques of IPC. And then, since it's a minimization of the summation of two CCP functions, we have mentioned it before. If we have proper regularity conditions, we can conclude that this f tilde and g tilde are CCP functions. Then we can use the DRS to minimize the summation of summation of these two CCP functions. So the DRS for this problem becomes we use this operator. Why we use the alpha in alpha -1? Because it's better to formulate the final form of the ADMM. And we use zeta k here, okay? We use zeta k as the variable here. So the first step is calculate the proximal operator of g tilde, and then is f tilde, okay? And with respect to this reflection, and then by the definition of DRS, we put them together, okay? It's not easy to analyze in this form, so we make a transform, we make a variable change, we define zk plus 1, zk plus 1 over 2 equals c minus bk y plus 1, and zk plus 1 equals to ak plus 2, and this, and use the identity 2, which means the identity 2, which is the proximal operator of the IPC is just a minimizer, just the minimizer of function, okay? So the DRS from these three lines becomes the following three lines, okay? So the first step is the argmin in y for this function, okay? This is the augmented function, okay? And then calculate the xk2, which is a minimizer of with respect to x of this, okay, is also a Lagrange, and then we update the UK. But here there is a small confusion here, because if you want to calculate the xk plus 2, you need the UK plus 1. But the UK plus 1 is next step. So somehow we need to reorder this iteration. And since you have, before this step, you have xk plus 1, which has a similar formulation. So we reorder it. We get this three lines update. First xk plus 1, zk plus, then yk plus 1 is the minimizer of this function, and then we update the UK, the door variable, okay? And we use the definition of the augmented Lagrange. First step is minimize this Lagrange in variable x with a fixed UK and yk and UK. Then we minimize the augmented Lagrange in variable y with fixed xk and UK. Then we update the UK plus 1, the door variable. This is exactly the alternating direct method of multipliers, okay? And this, how we get it? We get it from using the DRS for this unconstrained minimization problems, which generated by the infamous post-composition, which is equivalent to this primal problem. Okay, so this is the relationship between ADMM and the DRS. Okay, next we introduce a little bit about the splitting problem with more operators. Sorry. Okay, so now we consider about the inclusion problem with three variables. Okay, A, B, C are all maximum monotone, but C is single valued. Okay, by this equivalent statement, we say that if x is a 0 is the solution of this inclusion problem, we know that it is equivalent to say that Z is a fixed point of this operator T. T is defined by the composition of resolvent of A, resolvent of B, and C. Oh, no, resolvent of A and B, because we will use A, okay, so, sorry. So the Davis-in splitting is just the convex combination of the operator T together with the identity operator. Okay, so if we use the DYIs, okay, the Davis-in splitting method for the fixed point operators, okay, if we make some we expand this part, these operators, we can get this 3 lines iteration, okay? First, we calculate the resolvent of B, and then we use the say forward, okay? We use the operator say forward directly because we assume C is single valued, and then we put them together. And if it converges, if alpha belongs to 0 and to beta, and if the solution side is non-empty. Actually, this DYIs includes all the, not all, most of the splitting we mentioned it before. If A equals to 0, if the operator A equals 0, it becomes the backward forward. B equals 0, it's the forward backward. If C equals 0, it's the Douglas hash for the splitting. If AC equals 0, it's just the proximal point iteration, proximal point method, okay? Okay, so if we have more operator, what should we do? Can we use these splittings we introduced here? The answer is yes. So we use the lifting for the maximum monotone. Actually, it's a kind of techniques we use which in the product space, okay? We consider these problems. We want to solve these inclusion problems. Ti are maximum monotone from I to M. And if X is a solution of this problem, it is equivalent to say the both face X belongs to the 0 side of the both face T plus the normal cone of C. And the both face T is just we put the Ti to Tm together. It's actually the product of T1 to Tm, okay? And the C is the product space, okay, which the element is both face X and X equals to XX. All the elements are identity with each other, okay? So if we want to solve these problems, it is equivalent to solve the inclusion problems of summation of 2 operators. The summation of both face T, which is determined by the composition of T1 to Tm, and plus the normal cone vector, the normal cone operator of this diagonal subspace. Okay, this is an example of this lifting techniques, or it's called consensus technique. We want to solve the summation of the GI, okay, where GI CCP function. It is equivalent to solve summation of GI, but be careful. The variables are different, okay. For G1 is X1, for GM is XM, such that the both face X belongs to C. The both face X is X1 to M, and C is this diagonal space, okay. So with some regularity conditions, the optimal condition of this problem, or it's equivalent to solve this inclusion problems, okay. We have 2 operators. First operator consists of all the subgradient here, and the second operator is normal cone of both face X with respect to the diagonal space subspace C, okay. So we can use the DRS for these problems, okay, because we have 2 operators here, the normal cone and the subgradients. So actually the resolvent of the normal cone is just the projections, but the projection to say this diagonal subspace is trivial. It's just the average, okay. So the DRS can be written this way. You can calculate the proximal operator of GI actually independently, then you put them together, okay, as in the product space. Actually, we have another property of the of the Douglas-Hushford method, which explains why it is very popular and also very important, which is that it is the unique Fugol, sorry, there is typo here. It's a Fugol, okay, resolvent splitting without lifting. Splitting scheme is called resolvent splitting if it is just use the resolvent of A and B. It's a Fugol if it's just use the resolvent once in iteration without lifting, which means the operator which you use in the fixed point iteration is just in the original space, not in the product space, okay? For example, this FBS is Fugol because you use the resolvent only once in each iteration, but it's not a resolvent splitting because instead of only using the resolvent, you use the operator A directly, okay? This is not the resolvent. So this is Fugol, no lifting, but not resolvent splitting. We say that for solving the inclusion problem with one operator, the PPM is a unique Fugol resolvent splitting without lifting. DRS for solving the summation of A plus B is the unique one. It's the unique Fugol resolvent splitting without lifting. So it means for this for this inclusion problem with two operators, the DRS is the simplest, or the you can not find a simple one which is more simple than the DRS, okay? And then because of time, I need to say this quickly. Last, we introduce the projection type splitting method. Actually, this kind of family of method can also solve the inclusion problems with many operators, like not only 0 belongs to A plus B x, but also solve the 0 belongs to the summation of Ti from 1 to m, and the Ti are maximal monotone, okay? But in another perspective of projection. We recall that to solve these inclusion problems, we can use the PPM, okay? And the PPM can be regarded as a projection method, which we have analysis before. First, you need to find a pair Vk plus 1, Xk plus 1, okay? And then you define a half space, okay? Or not half space, hyperplane by Xk plus 1 and, sorry, this is Vk plus 1. There's a table here. This should be Vk. You define the hyperplane which by this pair, and then you project the Xk onto this hyperplane Hk plus 1. This is totally equivalent to the PPM. On the other hand, you can see PPM is a projection method. And this hyperplane separates the Xk and the solution site strictly. Okay, so it is natural to ask for these problems, okay, if we want to find the 0 belongs to A plus B, okay, this should be 0, and the AB are maximal monotone. Is it still, or can we still find a hyperplane which can separate the solution side and the Xk, which we can use a kind of projection type method for solving this A plus B? Okay, the answer is yes. Okay, but we need to do it in a higher dimension space, okay, for this solution problems. For one solution problem, the 0 set of A is just I write it here. For this problem, the 0 of operator A is the fixed point of the resolvent of A, okay? So we have, because the resolvent of this fixed point set is closed, is convex and closed, so we can immediately know that this zero side of A is closed and convex. But for A plus B, this conclusion, we cannot have this conclusion immediately. So we need to define this what we call the extended solution side, okay, which is called SE with A and B, which is in a higher dimension. So, okay, we use the dimension, we use the notation here in the Hilbert space, but you can put it in the finite dimension without any difficulty, okay? First, we define this extended solution side, okay? We have a property of this extended solution side. If there is a solution, and then there exists a W, which this pair belongs to this extended solution side, okay? And then we can also prove this extended solution side is closed and convex in this product Hilbert space. And the next step, because now we already have a solution side which is closed and convex, then we want to find the hyperplane which can separate the SEAB and the current point. Okay, since we know that the hyperplane is defined by a fan function, so before we define the hyperplane, we need to find that exactly a fan function. So first we define this phi ZW, which is the summation of these two inner product. Okay, we assume XB belongs to the graph of B, and YA is the graph of A. We define this linear, okay, this fan function of Z and W in this way. And actually, we can prove that if we define a half space H by this bilinear this fan function, and the extended solution side is just belongs to this this half space, okay? And since you have a half space, you have a hyperplane of the boundary of a half space immediately, okay? So we can have this projective splitting method, okay? So first we have a point. Be careful, this point is not in the original space H, it's in the product space, okay? So we have a P0, okay, which is Z0 and W0. Then we find a point. XK, BK belongs to the graph of B, and YK, AK belongs to the graph of A. Then we define this this fan function. Okay, this is a fan function. It's a summation of these two inner product. And then, as long as you have this fan function, you can define the half space. Okay, and then you can compute the P bar K, which is Z bar K and W bar K. Just the projection of ZK WK onto this half space. Okay. And then, of course, you can do this kind of relaxation, which with this relaxation parameter belongs to 0 and 2, okay? You can get the next point. The key point of here is, as long as you have this pair, XK, BK, YK, AK, you can define this fan function. And this fan function are corresponding to a half space, which separate the PK and the solution side. Then you can project the PK to this separating half space, or the separating hyperplane are corresponding to this half space. Then you can do the relaxation. Okay, so we have some properties of this projective splitting method. First, if we assume that the extended solution set is non-empty, the relaxation parameter is, this should be less than 0, strictly greater than, strictly less than 2, okay? And if we have another further assumption about the function, linear function, you see, we need the function value at this point is greater than some constant times the norm of the gradient square, okay? And if we assume zk minus yk approaches 0, wk minus bk approaches 0, then we see that the zk, okay, these three sequence all converge weakly to the element of z infinity, w infinity, which is the element of the extended solution, okay? Which means the z infinite exactly solves the solution. Okay, this is the convergence property of this algorithm. But there is a disadvantage of these algorithms. These schemes here, okay, didn't tell us how do we calculate the xk or bk, okay, and the yk, ak, and this is not clear, okay, and this is what I said before. If you use the multi-valued operators, okay, it is more convenient for the analysis in mathematics, but not for the practical. So we have a more practical version of the algorithms. So the initialization is the same, projection is the same, relaxation is the same. The difference is how to construct the linear function, okay, and which can satisfy this assumption, okay, because we need to if we want the sequence converge, we need these assumptions hold. Okay, so we give some parameters lambda and mu, okay. If we want to construct this, we need to choose some lambda and mu and alpha k which satisfies this inequality, okay. So we want to find the unique point xk, bk, and yk, ak satisfies these two following equalities, okay. So first we find xk, bk belongs to graph of B such that xk plus lambda k bk equals to zk plus lambda k wk, and then find a pair of ak, yk belongs to A satisfying this equality. Then with this kind of with these two pairs satisfying this assumption, this equality, and these two this inequality and these two equalities, we can define this affine function, okay. And then we can calculate the projection as in the previous algorithm and the same relaxation. And this is a more compact form of the algorithm 2. Sorry, algorithm 2 is this. This is algorithm 2 in the projective algorithm. Okay, so this is the same. This is the same. Here you can calculate this sigma k equals to this form, and you will have a closed formula of this zk plus 1 and wk plus 1. Okay, this is the more compact form. And actually, these algorithms can include some other kind of algorithms, such as the DRS, the Douglas-Hushford splitting method is a special case of these algorithms, and also the Springer method is also which is called the method of partial inverse. It's also a special case of this projective method. We assume that A is a maximum monotone operator, okay, and V is a closed vector subspace of the whole space. And we consider this problem. We want to solve these inclusion problems with X belongs to the V and and X star belongs to the it's a complementary space. So the Springer proposed this. We use the PPM to solve the partial inverse, actually to solve the problems with respect to this partial inverse operator, okay? And the partial inverse operator defined in this way, okay? If X star belongs to the graph of A, and then this pair, okay, the projections of summation, these pairs of summations, projections of summations belongs to the graph of AB, okay? And then to solve the to solve the inclusion problems of the partial with the partial inverse, which defined here, okay, which we define here, we can use the PPM, okay. This is a relaxation version of the partial inverse. First, we calculate the pk. It's just the summation, which is just the resultant of summation xk plus the x bar k. And then we calculate the pk bar, okay? And then we calculate the projection of pk bar and pk. And then we can get the xk plus 1 and xk plus 1, x bar k plus 1. Okay, and we know these schemes converge if we assume that this the summation of lambda times 2 minus lambda k equals to infinity. Okay, then we can prove that the projection of vk minus xk approaches 0, and the projection of k bar p bar k minus x bar k approaches 0. Okay, if there is a solution x. Okay, if there is a solution x of the inclusion problem with respect to the partial inverse, then the xk approaches x, and then xk minus x bar. Okay, the xk minus x bar. Actually, not only this Springer splitting, but also the Douglas-Hartford splitting is a special case of this of this projective splitting method, okay, of this projective splitting. The key idea of this projective splitting method is how do you construct this a fan function, okay? This is a fan function. So if you can construct another fan function, and also you can have a corresponding hyperplanes, corresponding half space or corresponding hyperplanes, and you can do the projection as the same here. So I think there are still a lot of things can be done which are related to this kind of projective splitting method, such as maybe we can use this kind of projective splitting method for convex combination problems. As we mentioned before, okay, if we use the DRS for the convex combination problems, we can derive the alternating projection ADMM. Okay, we can derive this alternating direction method of multipliers from the DRS. Maybe we can also make some applications of this kind of projective algorithms, projective splittings, also for convex combinations. problems and get some better algorithms. Okay, so this is all what I want to discuss in this class. We have discussed maximal monotone operators, proximal point method, and then the splitting method. Actually, this kind of scheme is a more abstract perspective of to understand or interpret the optimization problems, okay? Because we have derived that many algorithms we are familiar with is a special case or just applications of the proximal point method or Douglas-Ashford method. So it's a higher perspective to understand many optimization problems. So I think this is a motivation I want to give this mini course. It may help us to understand what we have studied before better. So this is, and later this, and the reference, and I didn't put all the reference here. I need to emphasize again, this book is a very nice book, and I used a lot of materials from this book, which has a lot of good exercise, a lot of very nice examples. It's very friendly for reading. And also the second book is a book about, you can find a lot of results about the monotone operators, okay? And second is a classic book. So this is all I want to discuss in this class. And finally, I hope I can see you guys in the workshop in FGV in the May to honor the birthday of Alfredo. Ok? Tá bom.